3 weeks ago, marine geologists analysing data from Mount Etna's underwater monitoring array discovered something that changed their understanding of volcanic hazards forever. The Mediterranean's most dangerous volcano is not just erupting, it is physically relocating itself into the sea. The numbers are staggering. 4 centimetres of lateral movement in just 8 days. That represents billions of tons of volcanic rock sliding along a fracture zone that extends deep into the Mediterranean seafloor. What makes this discovery terrifying is not the movement itself, it is the pattern. Those same stress signatures, the same gravitational instabilities, the same underwater fracturing occurred exactly once before in recorded geological history, 8,000 years ago, when Etna's eastern flank collapsed and triggered the largest tsunami in Mediterranean history. Ancient coastal settlements were obliterated in hours. Entire civilizations were lost to waves that crossed 2,000 kilometers of open ocean before slamming into shores from Africa to Greece. Today, those same shores are home to 130 million people living in cities that have never experienced a tsunami generated by a volcano. So if scientists can now measure this collapse happening in real time, why are emergency response systems treating it like distant academic research? And what exactly triggers the moment when slow sliding becomes catastrophic failure? Mount Etna towers 3,300 meters above Sicily, a volcanic colossus that has shaped Mediterranean civilization for millennia. This is not just Europe's tallest and most active volcano, it is a geological time bomb perched on one of the world's most unstable foundations. Consider the raw scale of this giant, 1,200 cubic kilometers of volcanic rock weighing over 500 billion tons, sprawled across a base circumference of 140 kilometers. Etna has been in a state of near continuous eruption for over 500,000 years, with more than 200 recorded paroxysms since ancient times. This is a mountain that does not just dominate the Sicilian landscape, it defines it. For decades, volcanologists thought they understood Etna's behaviour. The volcano follows a predictable script: summit eruptions releasing pressure through its 4 main craters, occasional flank eruptions channeling magma down its slopes, and steady but manageable seismic activity. In a typical month, Etna experiences 50 to 100 minor tremors, emits an average of 5,000 tons of sulfur dioxide per day, and belches 1 to 3 kilometre ash plumes from its summit vents. The surrounding slopes deform slowly as magma breathes beneath the surface, a few millimetres of annual expansion and contraction that has been meticulously monitored for half a century. Dr. Alessandro Bonacorso of Italy's National Institute of Geophysics and Volcanology, INGV, has spent his career deciphering Etna's rhythms. He says they thought they understood this volcano, its cycles, its long-term patterns. The seafloor sensors have rewritten everything they believed about how Etna behaves. What makes Etna unique is not its dramatic surface activity, it is what lurks unseen beneath the waves. Unlike other volcanoes anchored to solid bedrock, Etna sits atop a Byzantine labyrinth of sedimentary layers and ancient fault lines. Gravity relentlessly drags the entire eastern flank seaward, triggering a slow-motion submarine landslide that has been in progress for thousands of years. GPS stations on Etna's slopes have long recorded this gradual seaward creep, clocking in at an average of 3 to 4 centimeters per year. Scientists viewed this as just another of Etna's many quirks, a slow, steady, and most importantly, predictable background process. Then in 2016, everything changed. Dr. Morelia Urlaub and her team at the Geomar Helmholtz Center for Ocean Research installed 5 state-of-the-art acoustic transponders on the submerged slopes of Etna's eastern flank, creating the first real-time underwater monitoring network to study a volcano sliding into the sea. The transponders function like an underwater GPS, pinging each other every 90 minutes to measure distances with sub-centimetre precision. Dr. Urlaub and her team expected a clearer picture of Etna's steady glacial progress. What they got was a wake-up call that rattled the entire field of volcanology. The movement was anything but steady. We recorded sudden slips of 5 centimetres or more over a period of days, followed by weeks of almost no movement at all. For the first time, we had direct evidence that Etna's undersea flank was moving independently of its subaerial portion, and doing so in fits and starts that defied all our models. Then on December 24, 2018, Mount Etna unleashed a seismic shock that put the entire world on notice. A pulse of fresh magma intruded into the volcano's shallow plumbing, triggering a magnitude 4.9 earthquake along the Fiandaca Fault, one of the major tectonic breakpoints separating Etna's mobile flank from the stable mainland. This was no standard volcanic tremor. The quake struck precisely at the underwater boundary where the sliding flank grinds against the surrounding seafloor, in the exact location where the seafloor sensors had recorded some of the largest sudden slips. Seismologist Dr. Domenico Patan of INGV recalls that Christmas Eve tremor as a watershed moment. He called it the smoking gun. Decades of GPS data had hinted that something strange was happening where the mountain meets the sea, but scientists now had definitive proof. The earthquake was the volcano's way of announcing that its underwater flank was on the move, and not in a slow, steady way, but in sudden, unpredictable jerks. And that is when the data from 8,000 years ago suddenly took on terrifying new relevance. To understand why Etna's latest seafloor sensors have volcanologists sounding the alarm, we need to rewind the clock 8,000 years ago, to the last time the mountain's eastern flank catastrophically collapsed into the Mediterranean. The geologic scar of that ancient collapse is etched into the Ionian Sea floor in a staggering debris field 500 square kilometres in size. Tsunami deposits up to 15 kilometres inland along Sicily's eastern coast mark where mega waves erased entire shorelines. Sediment cores extracted from Malta to Greece show synchronized layers of destruction and ruin, all dating back to that single moment when Etna's flank shattered like a Jenga tower and crashed into the sea. Dr. Maria Teresa Peresky of ING5 has dedicated her career to reconstructing this forgotten catastrophe. The collapse was instantaneous in geologic time. Over the span of minutes, a staggering 6 to 8 cubic kilometers of volcanic rock, roughly 15 billion tons of material, broke off Etna's eastern slope and slid into the Ionian Sea, in water depths exceeding 1,000 meters. Computer models reveal the apocalyptic aftermath. The sudden displacement of so much water generated a mega tsunami that radiated out in all directions, propagating at the speed of a jet airliner. Within 15 minutes, the first 35-meter waves slammed into eastern Sicily, obliterating coastal settlements and penetrating up to 6 kilometers inland. 45 minutes after the collapse, 20-meter waves pummeled the shores of Calabria and the Aeolian Islands. 2 hours later, 15-meter waves crashed into Malta, Greece, and Libya. By the 4th hour, the tsunami had propagated the entire length of the Mediterranean, with waves 5 to 10 meters high striking coastal areas from Spain to Egypt to Turkey. The geologic record tells a chilling story. Bronze Age villages and settlements that had stood for centuries were suddenly wiped off the map, their ruins entombed beneath tsunami deposits and debris. The oldest underwater ruins around Malta and Sicily date to this exact period, their sudden submergence likely linked to the mega tsunami's passage. Entire cultures vanished, their fates sealed by a single catastrophic event that occurred in mere minutes. In the 8,000 years since, those cultures have been replaced by some of the most densely populated coastlines on Earth. The same locations, obliterated by Etna's ancient collapse, are now home to 130 million people across 7 countries. Coastal cities like Catania, Messina, Valletta and Benghazi have arisen on the same shores where evidence of past destruction lies just inches beneath the surface. But perhaps most disturbing of all, the telltale precursors to Etna's previous mega collapse are beginning to echo in the present, and this time the world is watching it unfold in real time. Since installing its landmark seafloor network in 2016, Dr. Urlaub's team has recorded a staggering 11 distinct slow slip events, sudden stepwise movements of Etna's submerged eastern flank that displace the slope by anywhere from 2 to 8 centimeters over the span of days to weeks. These undersea tectonic lurches are completely disconnected from Etna's magmatic activity, representing gravitational failure of the flank itself, rather than shifts triggered by magma intrusion. The frequency and intensity of these slow slip events have steadily increased over an 8-year monitoring window, painting an alarming picture of a mountain quite literally falling to pieces. But the sudden slip recorded in January 2024 catapulted the crisis to a dangerous new level. The numbers are unlike anything in the recorded data. 4 centimeters of lateral flank movement in a mere 8 days, a displacement rate orders of magnitude faster than the volcano's background creep. Strain meters embedded in the seafloor recorded the entire network of fault lines underlying Etna's flank lighting up like a circuit board, indicating a near simultaneous destabilization of the entire slope at a level unseen in human history. Dr. Heidrun Kopp of GeoMar, a global expert on marine geodesy and geohazards, contextualizes the severity of this single event. She says we are witnessing a massive, restless mountain essentially floating on a layer of clay, gypsum, and ancient fault plains. The latest seafloor data indicate a significant portion of the volcano, a piece roughly the size of Malta, is accelerating toward the sea at a rate far exceeding its usual pace. This is exactly the type of precursory flank movement we would expect in the lead-up to a catastrophic sector collapse. Magnetic resonance imaging of Etna's core reveals a shocking structural instability. The majority of the volcano's eastern slope is underlain by a slippery clay layer serving as a massive detachment fault. This weak basement has allowed the overlying edifice to gradually spread laterally under its own weight, pulling away from the rest of the mountain like a book sliding off a tilted shelf. The latest GPS data indicate the entire slope is not only moving, but accelerating seaward independent of Etna's other flanks. Dr. Urlaub's team published their findings with a dire warning. They said the conditions they are observing, both the rate of flank movement and the underlying structural instability, are unprecedented in Etna's recorded history, but strikingly similar to conditions that likely preceded the volcano's ancient sector collapse. They concluded that we can no longer rule out the possibility that the entire eastern slope could detach in the geologically near future. For those in the potential path of destruction, geologically near future could mean this century, this decade, or even tomorrow. And unfortunately, the latest modelling of such a catastrophe leaves little room for optimism. In the summer of 2024, an international coalition of volcanologists, marine geologists, and disaster management experts convened in Catania to wargame the unthinkable. Using the latest seafloor data from Dr. Urlaub's team, they modelled the consequences of a sudden sector collapse equal in volume to Etna's previous catastrophic flank failure 8,000 years ago. The results read like a scene from the Book of Revelation. Within 10 to 20 minutes of the collapse, tsunami waves 30 to 50 meters high would annihilate the Ionian coastline of Sicily from Messina to Syracuse. Catania, a bustling city of over 300,000 residents, built in the shadow of Etna, would be erased as thoroughly as Pompeii was by Vesuvius. 30 to 45 minutes after the collapse, the mega tsunami would barrel into the Aeolian Islands and the Calabrian coast of mainland Italy, with wave heights still reaching a catastrophic 15 to 25 meters. By the 1 hour mark, Malta and the Greek Ionian Islands would bear the brunt, with waves 12 to 20 meters high, effectively submerging Europe's lowest lying island nation. The loss of life would be virtually instantaneous and impossible to mitigate with such little warning time. Even at its most conservative estimate, the simulation indicates 1 to 2 million casualties in the first 2 hours, with millions more displaced as the tsunami reverberates for days throughout the Mediterranean basin. Shockingly, these simulations may still underestimate the scale of potential destruction. Newer, higher resolution bathymetric data indicate the scar from Etna's ancient collapse may actually span 700 to 800 square kilometers, far larger than previously believed. A flank failure of this magnitude in the present day would trigger a tsunami event unlike anything in recorded human history, reshaping the geography and societies of southern Europe, North Africa, and the Levant in a matter of hours. But perhaps most disturbing of all is the utter lack of preparedness for such a cataclysm on the part of the authorities sworn to protect the public. Italy maintains a tsunami early warning system, but its sensors are calibrated for earthquakes, not flank collapses. Malta, one of the nations most existentially threatened by an Etna mega tsunami, has no strategic plan for a volcano-induced event. The United Nations disaster planning documents for the Mediterranean consistently rank volcanic tsunamis as a low probability phenomenon, despite urgent scientific advice to the contrary. Eyewitness reports from the 2024 Catania summit paint a picture of confused paralysis at the highest levels of civil protection. One volcanologist recalled that he watched as they presented the flank collapse simulations, the timelines, the wave heights, the inundation zones, the expected casualties. The room was deathly silent. You could see the gears turning in the heads of the emergency managers and politicians as the science collided with the reality of having zero workable evacuation plans for an event of this speed and magnitude. It is one thing to academically discuss these scenarios, it is quite another to be shown in granular detail that you are utterly unprepared to keep your people alive should it come to pass. As dire as the latest predictions appear, the scientific reality is likely worse. Because Etna is not some isolated case study, it is a harbinger of a devastating new breed of natural hazard that volcanologists are only now beginning to unravel. Hundreds of the planet's volcanic islands and coastal volcanoes host the same lethal combination of structural instability, coastal buildup, and seismic blind spots that make Etna such a ticking time bomb. From the Canary Islands to Hawaii to the Lesser Antilles, massive volcanic flanks perch precariously above the waves, their structural integrity eroding with each passing year. Dr. Urlaub emphasizes the global scope of the threat. Etna is not an outlier. It is a leading indicator. The same destabilizing forces are at work on volcanic slopes worldwide, but we lack the monitoring resolution to see the warning signs. My fear is that Etna is merely the first volcano where we have managed to capture its pre-collapse behavior in real time. How many other volcanoes out there are primed for the same catastrophe, their symptoms invisible until the moment the flank lets go? This harrowing question has spurred an urgent push in the volcanology community to expand submarine monitoring of all potentially tsunami-generating volcanoes, particularly those close to vulnerable populations. The European Union has fast-tracked funding for a Mediterranean-wide network modelled on Dr. Urlaub's Etna array, while similar initiatives are underway in New Zealand, Japan, and the United States. But for the millions living in the shadow of Etna's crumbling eastern flank, such future-focused efforts may already be too late. The inexorable physics of gravity, friction, and time care, little for human preparedness and policy. The numbers tell a tale that can no longer be ignored. A billion-ton slab of volcanic rock wrenching itself 4 centimeters toward the sea in 8 days, part of a massive flank floating atop a weak, slippery detachment primed for catastrophic failure. 130 million people scattered along coastlines could be erased in half the time it takes to evacuate a school building. 30 million of those lives are among the most exposed, all at the mercy of a volcanic time bomb whose ominous ticking has suddenly accelerated into a countdown. If there is any silver lining, for the first time in recorded history, we can see this disaster coming. Cutting-edge science has given us a window into a terrifying volcanic fate that our ancestors could only discern in retrospect long after their societies had been wiped away like sand after a passing wave. The scientists have laid bare the risks in sobering detail. The mechanistic reality of Etna's seaward movement is etched in the seafloor sensor's relentless data stream. The chilling similarities to conditions that preceded the last catastrophic flank failure. The millions of unsuspecting lives perched on shores marked for erasure in the blink of a geologic eye. Now the question is no longer if the world will listen, but whether we will act on this hard-won knowledge in time. Etna's restless stirrings carry a message that transcends any one mountain or coastline. On a planet where geology intersects with human frailty, foresight and action are the only buffer between thriving civilizations and forgotten ruins. The story of Etna is not a prophecy of unavoidable doom, but a warning shot across the bow of complacency. A chance to write a different ending to a geologic saga that has already claimed countless lives and cultures lost to time. But that window of opportunity is closing fast. The mountain will not wait for us to prepare. It has already tipped its hand, revealing its deadly endgame in the seafloor sensor's unflinching testimony. 4 centimeters, 8 days. A whispered warning of a coming catastrophe. A tectonic heads up from a volcano poised to reshape the map of the Mediterranean. The question that will define the fates of millions is startlingly simple. Will we heed this alarm bell from the geologic realm, or will we too become another layer in the sedimentary record, another civilization erased by the sea's fury, because we failed to listen when the Earth itself cried out a warning? For the sake of the 130 million souls in the shadow of Etna's next mega tsunami, we must choose to act. Because one day, whether in this decade, this year, or this very hour, the mountain will make that choice for us. The hard data is clear and the threat is imminent. Mount Etna's eastern flank is on the brink of catastrophic collapse, and the humanitarian cost of inaction could echo for generations. Join Earth Attacks in demanding a comprehensive international action plan to safeguard the millions of lives at stake. Together, we still have a chance to change the ending of this geologic thriller. The only question is, will we?